this real. All right.
Also, hi, Robert.
Yeah. Hello, Robert.
All right,
Okay.
cool. How are we doing today, everyone? Doing good. Tired? Everyone's tired. It's mid-November, and you're at a university. Everyone is just so tired.
Plus magnetic storm.
Plus solar storm. Yeah, the solar
That's
storm.
what it's the ion is here. I knew it.
Cool. So I'm gonna finish up my talk today on kind of building hyperbolic angular momentum. And so I kind of want to recap what I've done over the last 2 days or the last 2 lectures. So we first talked about harmonic oscillators, and we kind of had the structure. And I'll recap this in kind of a different way than I presented it, based off of a re-lecture that I gave this earlier this week. And so we can talk about like the energy of the system, specifically for the harmonic oscillator, given the Schrodinger equation for it. So the Schrodinger equation, loosely speaking, is, or not loosely speaking, this is mine. The Hamiltonian acting on my function or my state gives the energy of the state and returns the function. This is an eigenvalue problem. And this is the basis of all quantum dynamics, or most quantum dynamics when we start talking about stuff like this. And so my Hamiltonian equals K plus U, or this is the kinetic and the potential energy. And I wrote this out as minus h bar squared over 2m d squared by dx squared psi, or maybe I'll say just d squared by dx squared. I'll make this a whole operator. Plus 1 over 2m m omega x squared on psi gives the psi. So this is the Hamiltonian specifically of the harmonic oscillator, and then it yields the energy. Harmonic oscillator is quantized, right? I showed that I can more or less factor this out into operators. So I had an A dagger operator and an A operator. And I showed that when they act on this state, so I'll write it like this, A dagger acting on my function, specifically, if I want to measure the energy of this. So I'll call this a state. Originally, we get E psi, but this gives me E plus h bar omega on my state. And if I were to do the same thing here, acting on now the lowering of the state, I get a lowered energy. I maybe can call this psi n, but I'll leave it here for now. So these are why these are ladder operators. They raise the measured energy or lower the measured energy of the solution here, or the solution state here. Any qualms or questions so far recapping this? Cool. Since this is being raised by a discrete amount or lowered by a discrete amount, and this is integral, we can kind of demonstrate a couple of things. Specifically, I can label this as psi n, such that if I measure the energy on this, I get the specific energy amount. So this goes up a level of energy. There's certain energy levels. So if I measure a certain energy psi, I should get out that energy value essentially. I labeled this specifically as just n, where this weird looking parenthesis thing more so notates this as a function in a vector space or a function space here. And instead of having h, my linear or a certain combination of these gives me this energy. Specifically n, where n is A dagger A, gives me this. N on my state gives n on here. So this is a very kind of abstract notation, but this is saying that A dagger A acting on phi sub n should yield the energy level, or I should say maybe H on this gives E sub n So what I was saying, that's not what I was saying. This is my H. So acting on this yields out my energy level.
These events, we could write these also specifically, right? It's E plus some integer multiple of.
Yeah, so A dagger was, at least in my notation, this notation is different depending on who writes these notes. 2 H bar M omega, I P, this is minus I P, plus M omega X, and A equals, remember the square root 2 H bar M omega, positive I P plus M omega X. There's a minus sign here and a positive sign here, or I just don't write. So using this construction, we kind of had this structure that I then just very abstractly started writing like this. And I also had that A on my state equals the square root of N on my state and A of N minus 1. Right. The ladder operator goes down and then A dagger on my state goes up. And my 3 factors N plus 1. So that was our first lecture. These were the things that we developed and then kind of recapped at the beginning of the second lecture. The second lecture then dug into angular momentum. So I'll get rid of some of this. I'll leave maybe this stuff so we can think about it a bit. So I talked about angular momentum as being a vector of operators. So it's a JX operator, a JY operator, and a JZ operator. And specifically, these satisfy a set of commutation relations. Specifically, JI, JJ equals I bar epsilon IJK J.
I'm slapping the thing.
What's the, is there a question?
I love the eyes.
The
JI and IH bar.
Yeah.
Yeah,
They're not
JI,
like
JJ,
two.
JK, JK, II, that's just all over the place.
Yeah.
Maybe LMN would have been a better indexing set or ABC or
That's right.
something.
Yeah.
We'll go with convention here. Any set of operators that satisfy this are what we can call a quantum angular momentum system. So these operators satisfy this, where I define JX, JY, and JZ, almost like classical angular momentum, right? L equals R plus E. I then derived some similar structure for JX, JY, and JZ, and posited this commutation relation. I also mentioned some important things that we look for. For instance, we look for the squared angular momentum, J squared, which is J dot J. So JX squared plus JY squared plus JZ squared. And we fix an axis and study its specific angular momentum. By convention, this is the z-axis. So JZ, such that these two commute. It's not a such that, these commute just by the structure of J squared, right? JZ, like so, I can kind of demonstrate this very quickly. Y squared plus JZ squared, JZ, right? JZ with this JZ squared term automatically goes to 0. And then whatever the commutation I get from this JZ with JX type thing here, I get the opposite with JX and JY there. So they are like canceling each other out. So this goes to 0. And because these are commuting operators, they share an eigenvector. For lack of going into too much detail with it, typically, since these share an eigenvector, they're expected to have different eigenvalues based on which one I'm using to measure. So I'll say, maybe I can label my state or my function or whatever with lambda and mu, and I'll say that J squared on this should give me lambda on lambda mu, and JZ on this state to give me mu on lambda mu. And another thing that's convenient from this algebraic structure here is I can compose ladder operators. J plus, I'll define as Jx plus I Jy. J minus, I'll define as Jx minus I Jy. And they act in the following way. J plus on lambda mu to give me some number out front, I'll call n plus, on lambda mu plus 1. And similarly, J minus on lambda mu will give some n minus on lambda and mu minus 1. I specifically picked mu. I could have picked lambda, but in this structure, we'll say that is mu, and that comes from a little bit of analysis as to why mu instead. Typically, we don't see this lambda mu as being what is written though. If you've ever seen any sort of course on quantum mechanics, or even if you haven't, I'll just say it. We typically write this state instead as Jn. J is spin and has non-negative half integer values. Non-negative half integers. And m sometimes it's called the magnetic number, but I'm just going to call it the z component. And it runs in integer steps from minus j to positive j. And again, we can show the structure by doing some analysis on this operation here. And it's also very useful to note Jz here, its spectrum is bounded by the spectrum of j squared. So j squared, its spectrum is labeled by these j components. These m values are bounded based off of what I can get here. So that's useful, that boundedness of that operator there. That specifically has kind of that boundedness versus non-boundedness of what I'll show are the hyperbolic operators has kind of thrown a wrench in the system a little bit because those non-bounded operators don't behave as nicely.
And what does that vector represent exactly? A particle?
Yeah, like it can talk about the like the state of a particle, for instance. So it can talk about the squared angular momentum of the particle and the possible z components that I could measure from that.
But not just a particle or something else too, or what?
Here specifically, like I could talk about the angular momentum state of an electron, for example. So J is 1/2 in this instance. I get -1/2 or +1/2 as my possible n measurements.
You don't care about position of it or momentum, just only how it rotates. I mean,
Yeah.
so-called rotates.
So-called rotates, but this is just an intrinsic thing. It doesn't have a classical analogy here. Cool. So those were the two things that we had put together over the last two lectures. And now I want to join these ideas together. Specifically, I have a system of ladder operation here. I have a system of ladder operation here. And I can not necessarily, I don't want to say abuse, but I can kind of enact this Jordan-Schwinger map. What the Jordan-Schwinger map says here, and I'll demonstrate this, is that I can map these ladder operators here as some combination of these here, maybe in multiple spaces. So first I'll kind of demonstrate something visually. I want to talk now about two harmonic oscillators. These are going to be disjoint. So what does that mean specifically? I want to have maybe an A oscillator that acts in the following way. I'll have NA on my state NA, which gives the maybe energy of that state, that in A, which is the same thing we had earlier, n on n gives n on n, but instead restricted to A, so defined on A specifically. And then I get the ladder operators here. And a dagger on this state is in A +1 and A +1. And I also have a B oscillator. Another important commutation relation that I might not have mentioned, a dagger equals 1. This also goes with the discrete nature here. So there's an A oscillator, and I want to introduce a B oscillator. So in B on my NB state will yield that NB energy level. B on NB. We'll do the same thing. I'm just labeling with NB instead. N+1 and B dagger on NB, which is the square root of NB +1 on NB +1. These being disjoint gives this, that A, B equals A dagger, B dagger, or any combination of these yields 0. So these all commute with each other. So any B commutes with A, or B dagger commutes with A dagger, or whatever. And these also satisfy independently that B dagger is 1. And so I can kind of map these such that I join them at a 0 here. Let's call this 0. So I'll let maybe in A run this way, and in B run this way. I can take it off.
Was this diagram given by Jordan and Schwinger?
No, this diagram is specifically introduced. Was it Kochik? Kochik introduced this diagram that helps to give a good visual representation of this. So I'm going to draw a part of this grid right quick. In Schwinger's paper specifically, he introduces a couple of things that'll make this grid make sense.
Before they, what does it mean again? You maybe didn't say like, what are these oscillators to be? Disjoint, independent? What is
That
what exactly
they-
do you mean?
Like they commute with each other.
Just
They don't-
formally, the operators commute.
Yeah, formally these operators commute, they're disjoint systems. That's what I'm gonna say
So
here.
they lead
That
next to
sounds-
each other but do not communicate, let's say, right?
Sure.
Yeah, that's maybe a good way to say it. Neighbors that don't like each other, they can work, but they just go past each other without saying anything. Cool. So in his paper specifically, Jordan introduces the following things. He says, I want to talk about J and M in terms of NA and NB. Specifically, he starts by defining J plus and J minus in terms of this A dagger, B dagger stuff. So he says J plus, I'll define as A dagger B. And there's an H bar in front, but I use natural units, so I'm just dropping H bar. Structure-wise, we just really want to look at this A dagger B. J minus, I'll define as A B dagger. And he says the following things about relating J and M. Says J is going to be given as NA plus NB, and M is going to be NA minus NB. Using these two equations, I could solve for NA and NB if I wanted to. NA is J plus M over 2. Actually, I think I might have these backwards. I think these are over 2. And then NA, yeah, that's it. Equals J plus M, and NB equals J minus M. This is the structure that he gives here. So now I can start talking about these angular momentum states instead as like basically two harmonic oscillators together.
Your J has to be half integer value.
Yeah, J is
So it doesn't have to
non-net.
be over 2.
These have to be over.
That's how you know this, right? Because your J has to be over, half integer value, right? So that's how you know that's the right one.
That makes sense.
Yeah.
I kind of don't think when I usually write these out to like
That's
do
just-
example computations. I just look at it and I'm like, actually, that doesn't, but that's a good way to think of it. So this is basically saying, maybe if I want to talk about lines of constant J. Well, first, on my NA line, to go up a step, I use a dagger, right? A dagger takes me from NA to NA plus 1. To go down a step, I use A. Right? It goes from NA to NA minus 1. B does the same thing, but on the B axis. And again, these are not like an axis on the same plane per se, typically. I'm just visually throwing these together like this. And so this is my A dagger direction. This is my B direction. And so if I want to go from this state to this state, where this line here is a constant J value with given M values. The M values are changing here. I didn't draw these perfectly, but
It's beautiful.
it's good enough. Maybe I'll use this draw and do this.
Well, and color.
Oh, there we go. So this is some fixed J value. I'll call it maybe Ji. And I have lines of fixed J value. So this is another line of fixed J value. This is another line of fixed J value. Another line of fixed J value, so on and so forth. And again, this is Kochik's interpretation of the what we put together from the structure here. This is a line of fixed J. Line of fixed J, line of fixed J. Maybe I said J is NA plus NB over 2. So NA here would be 1, NB here would be 1, 1 plus 1 over 2. This is the J equals 1, maybe. And so I have these fixed lines of J that are running through right
J
here.
is half integer value.
Yeah, J is half integer valued. So looking at this, I'm seeing that everything is going to be full integer valued. And so what is the problemo here? So they both start at 0, 0, and they both go to 1, 1. But like I have that and that go together. I won't label these just yet. But we're okay with fixed J, fixed J, fixed J. Like anywhere I move on this line, I get a fixed J. My M value, however, is changing. So this is some M value, and say I want to go up in M value. So this is M. I can go to M plus 1, go up again, wherever my next dot is, maybe here, M plus 2, M plus 3, and then terminate it here, and I can go backwards as well. So here, I can draw this off diagonal axis. This way is increasing my M values, and this way is decreasing my M values. So I get a J plus going this way, J minus going that way. So I can visually think about it. However, we also have this other axis here. And so if this was A dagger B, across from A dagger is A, and across from B dagger is B. And so this invites the construction here, just visually yet. We like, just from this visual structure, kind of jumped the gun on what Schwinger was doing in his paper. We're inviting another kind of set of, or I should say, they don't act on the axes. Right, this is A dagger, A, B dagger, B. So we're inviting another operator here, maybe I'll call it K plus, and another operator, A minus. So if these are fixed J with M increasing, then these other lines, conveniently placed other color chalk. Yeah. It's supposed to go through all the dots, but I can't draw it.
Sure it does.
Sure it does. Yeah, I'll tell myself that.
Well, One trick that I learned is you just make the dots bigger after you draw. it.
Yeah, like if the dot's big enough, then within some margin of error, I'm on the dot. Cool. So if these are fixed j and the m is increasing, I can pick an m value and then talk about all of the j that allow this m value. So the first idea that we had is say j equals, what's a good non-negative half integer?
Half.
1/2. Then by the structure of
The
m,
answer.
m is 1/2 and minus 1/2. But say I want to fix an m and talk about the corresponding j's. What's another good non-negative half integer?
Half.
3/2. 3/2. We're gonna be a little more creative. 3/2. And I can talk about what all j values allow an m value of 3/2. This is gonna be what? 3/2 allows that value, 5/2 allows that value, 7/2 allows that value, so on and so forth, going up in integer values. But like j equals 1/2 doesn't allow this, and so on and so forth. So I can talk about what j values allow these. So it makes sense that if this was going up in m or going down in m, as j does, j plus and minus, this is j plus or j. We're affecting j here. We have different j's and m's. This is a little confusing. Maybe notation could have been creatively designed better, but that's fine. So this k that I'm suggesting should, in theory, give me a j plus. And so I can define an algebra that does what I want it to do. Suggest you look maybe dissatisfied.
That's not J plus, right? J plus, I think
This
you
is the
said
j
it, you
plus
said it.
operator. This is j is going up. These are the values of j and
Little j.
the ladder for j. This is the ladder for n. It's a good distinction to make there. That this is specifically the m ladder. This is specifically the j ladder. But not like this is j plus, this is k plus. Again, maybe notationally we could have picked better things, but this was, destined for us like 100 years ago. So we're going to
Again, the question is why, what's the difference between K plus and J plus?
Yeah, so j plus, I have a dagger b, and its construction suggests that k plus should be a dagger b dagger. And k minus, I suggest should be a b, right? A and b should get k minus. So I want to see if these work. I'm going to take some arbitrary state, act on it by transforming it into this what we call Schwinger basis, and then seeing if I get something good when I turn it back out. So let's do that. I will erase this stuff over here because the pretty picture has to stay. There's something so satisfying about having diagrams like that and multicolored chalk. It's great. Oh, there's a comment in the chat. What is that?
Just hello.
Oh, cool. I just now noticed that.
Hello to you too.
So I can write my Jm, right, starting out with an angular momentum state as, well, I want to rewrite it as J plus M, J minus M, which is in A, in B. Specifically, notation was adapted because this was also Kochik's notation, which is a pretty solid notation. I personally tend to write it as almost like a tensor product, in A, in B, an implicit tensor product there. But that could also get like foggy if someone's reading this and they automatically assume tensor product here. So I want to rewrite my arbitrary JM state as this state, act on it, and then undefine it or untransform it basically. So I'll just arbitrarily say J and M. I'm not even going to attempt to put values to these. I can do this as abstract as I want. This is a math seminar. We love it. So this is going to be J plus M, J minus M. And again, I'll use this double notation Very nice, very convenient. And I want to act on this maybe with a J plus. I'll start with J plus. I'll show that all of these work. So J plus on this JM state, I know typically should give me the following. It should give me the square root J times J plus 1 minus M times M plus 1. There's an H bar squared out here that I'm ignoring again, or an H bar. And then this is J M plus 1. So by golly, I should get a very similar result. Just trust this result. This comes from doing a little bit of analysis. So I want to do again the same thing, but now with A dagger B on my J plus M, or I'll say in A and in B state. Cool. So what does A dagger do? It gives me in A plus 1 and B just by itself gives me in B minus 1. And there's some factors. I'll move them out to the side, but it doesn't matter if they're out front or out back. This should give me in A plus 1, and this should give me in B. And now that I've acted on this, I want to untransform it. So to go from in A, maybe I'll define this, maybe reverse transform. So I said that J is NA plus NB over 2. And N is NA minus NB over 2. So NA plus NB, that's NA plus 1 plus NB minus 1 over 2. And then their difference, NA plus 1 minus NB minus is plus over 2. And then I've got these prefactors out front. The square root of NA times NB. NA is J plus M. So J plus M plus 1 and J minus M. Cool. Then this is, allow me to use a little bit of room over here because I write big. I have J plus M plus 1. J minus M. This plus 1 minus 1 cancels. So just get in A plus NB over 2. And then plus 1 is plus 2. So I get in A plus in A minus NB plus 2 over 2. And boy howdy, I get the same thing. J times J plus 1 minus M times M plus 1. You can verify that these are equivalent if you want. And I get J and M plus 1. How convenient. How nice. And that is by design what we've got here. So I see J plus works. I'm just going to assume by structure that J minus also does the same thing. It looks to be good. But I want to show that K plus specifically works because it's a little more foreign. Typically, when you're going through a physics textbook or a quantum mechanics textbook specifically, the J operators are well covered. The K operators are not. And so, by studying the structure of these K operators, I will mention a little bit of the algebraic structure that is presented by the K operators, and I'll have to refer to my notes for the exact commutation relations. If you allow me a second. Here.
Well, people, did we get coffee? Perhaps?
Oh,
Is that a here?
Coffee has been made.
Copy has
We
been made.
one wants coffee now, but if not.
I've got my notes
Oh,
here.
if you found them, good.
Honestly.
Perfect.
would be perfect for the play.
Yeah.
So we get the following relation, and this is defined by Schwinger. K3, so right, I can talk about J as JX, JY, JZ, or J1, J2, J3. K3, or I'll do KZ since I've been doing that already. KZ, and then K plus or minus gives me k plus or minus plus or minus. And typically, when we're doing angular momentum, we get that, j plus j minus equals 2jz. But the structure that Schwinger suggests is that k plus k minus gives me minus 2kz. Motivate that a little more, but maybe not taking up too much time. So I'll just leave it as is. These can be given from these commutation relations. Specifically, I define k plus as kx plus iky and k minus as kx minus iky, similar to beforehand. But when I use these operators and such, I'm going to get these commutation relations when defining here. And jz can be found by like taking the jz can be found by taking this product and studying it a bit. kz can be found by taking this product and studying it a bit. But we also will notice, and this is where the hyperbolic nature comes in, is that k squared on this state gives kx squared minus ky squared minus kz squared. So by using these operators, we can get that structure there. And we also get these commutation relations. Kx with ky, jx with jy, we know is ijz, but here we get minus ikz. So get a minus sign there. Bit different from our structure that we had before. Ky with kz gives me ikx. That's to be expected. And kz kx gives me iky. So the commutations are good. This one, however, gives our minus sign, and so that's why we get a little bit of a different structure. And these commutation relations, I have these notes that I can like send out as an email that kind of better explain this with not such time constraints. But this structure here gives a similar thing. This structure also sometimes is written as k squared equals minus kx squared minus ky squared plus kz squared. It's almost like a signature at this point of how you want to do your k squared. But I want to say for our paper, we're sticking with this bottom signature. But when I first think about it, I just think the hyperbolic structure and get this signature here. Cool. So I want to verify that k plus does what I do. With this algebra, we're able to see that k plus on a jm state gives the square root j plus 1 squared minus m squared on j plus 1 m. And k minus on jm is the square root of j squared minus m squared on j minus 1 m. So, and these factors here are found by doing similar analysis that you do with the j plus and j minus operators. Again, very detailed in my notes on those there. So I just want to quickly show that this does the same thing. I need this. So I want to add this k plus on a state. So I'll say A dagger, B dagger on my NA and B gives me square root of NA plus 1 in B plus 1 NA plus 1 in B plus 1. Cool. And then similarly, I can kind of undo this transform back. It's going to be the square root of j plus m plus 1, j minus m plus 1 on NA plus NB plus 1 over 2, NA plus 1 minus NB minus 1 over 2, which gives, and you can verify this, I get the square root j plus 1 squared minus m squared, and then a j plus 1. Right, this plus 1, I get the NA plus 1, NB plus 1 over 2 gives that plus 1. And then here that plus 1 cancels the minus 1 there to give me the same thing. So structurally, I get that from the algebra described by Schwinger, right? Schwinger defines kind of part of this algebra. You can verify more of it with these operators. That this prefactor matches the prefactor here, and the states are altered in the same way. One thing that, if given the time, maybe after we like wrap up our project, I might want to sit and do this more analytically instead of looking at it abstractly, start looking at it like as the functions and really writing out all the details. There you have it. That is hyperbolic angular momentum, built from harmonic oscillators and basic angular momentum.
All right, thank you. Questions and comments?
Now, what happens if your A's and your A daggers don't commute with your B's and your B daggers? Does that totally ruin everything?
I'd imagine yes. So this more so is motivated by, I'd say second quantization is where the motivation of the structure comes from. So basically each point in space gets its own harmonic oscillator. You can talk about the wiggling of each point in space.
Mm-hmm.
And we can have the individual ladder operators for those harmonic oscillators. And by structure, all of those commute with each other. They don't interfere with each other, because otherwise you get a big mess. It would be interesting to look at like
so
an interfering
doesn't
system.
Failure of commuting means something about there's an uncertainty principle around?
Yeah, that would be like an uncertainty between one state and the state beside it. So I wouldn't be able to measure like,
So if you move up like A dagger and you measure that completely, you know nothing about B, for example.
say I can model a line in space as just a bunch of harmonic oscillators put together. For now, I'll just say there's 2 of them. This is harmonic oscillator A, harmonic oscillator B, that wiggle together. If these operators don't commute, then I can't talk about A without also talking about, like, I can't measure anything about A without changing what happens to
Yeah.
B, which completely alters the structure here. However, there's probably some intrigue in talking about if these do commute with each other. Not apart from a physical model, just mathematically modeling kind of what this would do. I haven't personally seen anything on that, but I think that'd probably be an interesting toy model to work with.
That's a nice suggestion. They slightly do not commit.
Yeah,
And the
yeah.
slightness of it, how does it influence the whole thing? You get maybe some series of
Yeah, if they like are within epsilon of commuting, can you get something here, for
Well, it
example?
will be bigger. No, it will grow, it will change.
It's a lot of really interesting physics is done when you start altering like fundamental commutations. And so over the summer, one of the other people that we were just listening to some research with was altering specifically the commutation of a dagger. This is usually 1 given from the XP commutation. But he was saying, what if this isn't 1? What if I get different types of commutation? What interesting mathematical models pop out of this?
I had a comment about this hyperbolicity of this. This looks exactly like the special linear group SL2 over real numbers, exactly the same structure. So the thing would be to find out in it. And once you find out in it, you will see there are crafty polynomials there.
This is,
Once again, yeah.
the structure that's usually used with this is the SU11 structure. But SL 2Z, yeah, there's
SS2R.
or yeah, a similar structure. Most of the time, this is used. SU11 builds what we call relativistic spin networks. And so this is a very useful way to quickly get that motivation, because spin networks, very loosely speaking, are a labeled graph, where the labels are spin that satisfy the Clebsch-Gordon conditions. And that labeled graph is in some way able to describe a quantized spacetime. If I use SU11 instead, it's a relativistic quantized spacetime.
Let's say baby relativistic, because this.
Yeah,
The space is only three-dimensional. space.
yeah. Instead of using an SO31 or anything like that, we shrink down to SU1.
Okay,
Other questions, comments, concerns, cries of outrage?
you no remarks?
I can say that maybe this representation is only one of the few that has been listed by Bergman, right?
Yes, so Bergman went through and did basically a characteristic study of this, and there are 4 different possibilities of more so the spectrum of this K value. So this is one of the 4, talks about discrete spectrum, continuous spectrum, and then the different components of those. So only positive or positive and negative spectrums. This gives the discrete positive and negative spectrum from the physical conditions that restrict it. We get a discrete system, which if you're interested, I also talk about a bit in the analysis of this.
Are there any experiments can be associated with it? Preferably very simple, so simple you can do them in your kitchen.
I don't think
With
so.
coffee, for instance.
With coffee? No, I don't think so. But I don't know if that's necessarily my job to figure out. I'm curious. So maybe, but I'm gonna say no. From the bottom of my heart, I don't believe so.
All right, so let's thank our speaker again. We can grab no coffee and gossip about this and everything else, right?
Yes, if you want me to send you the notes on this, I guess just write your email on the back of this article,
Okay.
and I'll send you an email of my
Oh.
CMMs and whatnot.
Do you want me to post it on next to your
just
talk? On
Oh, I can definitely do that.
Send it to me.
We should also stop the recording.
Post as an announcement on your EQL.